Okay, so this is a set of notes on using Gauss-Jordan in order to fit a polynomial curve to a set of data points. So the basic problem here is that we're going to be given a set of data points, so we'll call those x1, y1, x2, y2, all the way out to xn, yn. Now, somewhere in pre-calc, you should have gotten the idea that if I have n points in the plane, that I can fit a polynomial that is of degree n minus 1. So we're going to actually list this as a constant term plus the first term times x to the first, or just times x, right? Plus the second term times x squared out to a n minus 1 x n minus 1. Now I know that this seems backwards to the way you're used to writing a polynomial. People who do applied math tend to view a polynomial just as a sequence of numbers. So we actually ignore the fact that there's an x squared, x to the n minus 1, and we say, oh, this is the sequence that represents the polynomial, and we just use the coefficients. But to keep it real, we'll leave it like this for right now. All right, so what we're saying here is that each of these points will produce a linear equation where I have a0 plus a1x1 plus a2x1 squared out to an minus 1 xn minus 1. Oh, I gotta get some more room in there because that's gonna run off the page there. There we go, 3 dots plus a n minus 1 x1 n minus 1 is equal to y1. Now, it feels like that's a polynomial equaling y1, but it's not, because x1 is given to us, which makes these constants. And in fact, the a's are the variables in this equation that we're solving for. So a second equation could be made with the second point. So all of the subscripts here are now 2's, and then we just keep this going until we use all n x values. Equals and the nth y value. All right, so I'm going to get n equations, and I end up with ultimately 0 through n minus 1 is, well, n equations with n variables. Okay, so this is a system of equations, and in fact, if these points are functional, meaning that they are not, you're going to pass the vertical line test here, you're going to get a unique solution to this. All right, so ultimately, the solution to this system will give me the a0, a1, a2 that will form this polynomial. So let's give this an actual example. All right, so I want the polynomial, let's say I want a quadratic. A0 plus a1 x plus a2x squared. Now, you did a problem like this probably somewhere in Algebra 2 where you were given 3 data points. 1, 4, 2, 0, and 3, 12. Okay, so these are 3 data points that all have different x values. And I need to fit a parabola to this, right? So that means I have this system of equations where I have a1 or a0, right, plus a1 times 1 plus a2 times 1 squared is going to equal 4. a0 plus, let's see, 2 a1s plus, was that 2 squared is going to be 4 a2s is going to equal 0. And then a0 plus 3 a1s plus, let's see, 3 squared is 9 a2s is going to equal 12. Okay, so there's my system of equations. Using my data points, I can put that into an augmented matrix. 1, 1, 1, 4, 1, 2, 4, 0, 1, 3, 9, 12. And I can go ahead and do Gauss-Jordan on that. And that happens to come out, well, this should be 100100001 because it's going to have a unique solution. And the numbers come out as 24, negative 28, and 8. And I suspect that you could do the MATLAB work to do that because this is just a Gauss-Jordan problem, which means that my polynomial, p of x, is going to be 24 minus 28x plus 8x squared. And if you want to like break out a graphing calculator, you'll see that it happens to go through those 3 points. Now, the great thing about MATLAB is that at moments like this, there is a built-in function, right? So let's actually look and see how that works. Okay, so you're staring at my command window in MATLAB, and let's type in some commands. So we had these points, 1, 4, 2, 0, 3, 2. So what we're going to do is we're going to create an array of the x values, 1, 2, and 3. Oops, let's try that again. 1, 2, and 3. Aha, that's better. We're going to create an array of the y values, 4, 0, and 12. Now these are ordered, right? Because the 1 goes with the 4, the 2 goes with the 0, the 3 goes with the 12. The command in MATLAB to deal with this is called polyfit. And if I put the x values in as the first parameter, the y values in as the second parameter, and say fit it to a second degree polynomial. So like if I want a quadratic, I use 2. If I want a cubic, I use 3. If I hit enter, it returns a sequence of numbers. Now you're going to notice that this actually goes the way that you're accustomed to it going. So this is actually giving me 8x squared minus 28 plus 24, or minus 28x plus 24. So the folks that designed this thing actually made it come out from largest power to smallest, which is what you are accustomed to. So MATLAB does this all automatically with one command. So there you go.